In this video, we will learn one of the actual skills for you to be top AI researcher or engineer, and we are gonna be learning these skills over the next 1 to 2 years on my channel. Everybody thinks if you want to be the best AI or a top level AI researcher engineer, you need to be reading latest AI research papers. But guys, that is not true. In reality, you need to master fundamentals. So if I ask you not only what is the standard deviation formula, which is used everywhere actually, you need to understand why this formula, why not other formula, why don't I divide all of this by 3, for example, what will happen then? So these are the actual skills you need. And it seems like, oh my god, this is high school mathematics, but it's not true. No, it's not just that I feel like, but in reality, the best researchers know, understand, have deep intuition about these fundamental basic things. What does this root do? Why do we sum all of these, etc.? So these are the fundamentals, the high school, the early college or college mathematics that we need to master. And then you will know more than anybody who's like reading all of the papers, but who cannot implement any of the papers. And this is what companies like OpenAI and Google want you to be able to do. Like they want you to understand what's gonna happen if I remove some or add some other thing here or remove this root and stuff. This is because when you are trying to make AI better at reasoning, at coding, for example, first you will understand everything about that. But then when we talk about this specific thing, you will understand like if I add this number or this term here, how will it change the weights of the AI, the training? And then that training you will be able to imagine what it's gonna do, and you will know if this will improve the coding of the AI or not. Check this out. So I have a linear layer and then linear, input features 2, output features 3. So if we look at linear.weight.shape, it's a bit weird because it says 3, 2 is the shape of the weights, while here I say input 2 and output 3, so it's reverse. So if I say 4, it will be 4, 2. So let's go back to 3. If I say linear.weight, so this was just shape, but let's see the actual weights. It's 3 rows, that's this 3 and 2 columns, okay? So each row of weight is the weight for one output neuron. So we can see that this is the first for the first neuron. So when we have 2 input features, they get multiplied with this neuron, and 2 input features with the second neuron and with the third neuron. But when we multiply, I'll show you here. So let's first look at this x, and let me show x. So it's just one row, but we know that when we multiply this x with weights, we want to actually have this to be a column, so transpose. So we multiply row with a column, that this should be a column, because we want to multiply with this neuron but in a column. So we will make a transpose out of the weight, or linear. When we multiply it with linear, we will make a transpose. So PyTorch will automatically transpose this weights matrix. So now it's row times column. So I'm showing you this will happen automatically while the multiplication is happening in the linear layer, and the weights will be stored like this in reality. So they will not be stored when transposed and stored. So if I say y is x matrix multiply linear weights transpose, we can see now y is just also 1, but the output is 3. So this is input times first column, input times second column, and so input times first column, input second column, input third column. But this is the thing. So we have this y, that I multiply with just linear weights transpose. But if I pass x through the linear instead of multiplying it like this, we get different result. Why is the result different from y if I did the same calculation here times transpose matrix weights, and here should be the same? I'll tell you right now. So it's because actually this linear will also have this bias, so it will add this bias to the matrix weight matrix multiplication. So we will actually do y plus bias, let's see, and now it's same. But if I go and disable bias like this in the linear layer, then if I do all of this good stuff, we will get now same numbers without adding bias here. So when I add bias, but let me see, yeah, there is no bias. There is nothing here. So without bias, we just need to recalculate everything again, because the now weights are gonna change because I initialize linear layer again, so weights are gonna change, so we need to calculate everything again. Why not store weights as 2, 3? Because then each column would be a neuron's weights, which is weird to read, doesn't match how we think. Each row 1 neuron. So here in the weights, each row is 1 neuron, and we don't want to store it like this where each column is 1 neuron. We just want to multiply later with this transpose, but not store like that because it's not intuitive. Here we can actually create batch of x. So now we have 8 vectors and each vector has length 5. So we pass this through 5, 3 linear, and we just get 8, 3 result output, because now each of the vectors has been transformed from 5 elements to 3 elements by the neuron. So this is our x, and these are the weights. But when multiplying, it will be transposed. So you see, it just like this row is just now this column. So it will multiply. Let me put this up here so it's easier to see. This row with this column, and the output, is it y? It will be this row. So first row times first column, it will be this first number, and then first row second column will be second number here. So you see it's at the intersection. First row second column will be in the first row second column, and same for first row third column goes here. So that's how it goes. If we have x 4, 10, 5, so 5 in columns, and then there is 10 of those rows, and then 4 of those groups. So multiply by 5, 3. So it will just take this whole row, it will turn it into 3 numbers, because it will multiply with the first, second, and third columns. So it turns into 3 numbers, and the other shape is the same. There is still 10, and there is still 1, 2, 3, 4. So it will be same as this. For each element in ij, we multiply that element of x times the weight matrix plus bias. So it's just, for example, this element gets multiplied with the transposed and weights, and then it gets at the same position. same position. So ij is same, I and j. So if we have linear layer, it's 4, 2, and x is 3, 5, 4. So this 4 and this 4 should be same. You see the result is 3, 5, 2. That's the output shape. Input shape is x, which is 3, 5, 4. And weights matrix, it's gonna be reversed from this, so 2, 4. We explained this in the beginning of the video why. You can go back and watch if you don't get it. So now let's define our own custom linear layer. We have init, self, in features, out features, and bias. So just assign those variables. Now create weights, which will be out features, in features. So we multiply these random numbers by this scaling factor, and we'll talk more about this initialization types later. But this is to stabilize the training. I'll show you here. You see, without that, there is huge loss, 70,000, and needs a lot of steps to converge. But with that initialization, you see the loss is not that big at all. And you see, without that, we have huge numbers in the exploding activations, we'll see. But with that initialization, it's a lot smaller and more manageable. So it's easier to converge the loss here as well. But we'll talk more about that later. I just showed you that this makes it easier to train and to start the training, especially good initialization of weights. Then if bias, we will create zeros, and if no bias, then not create anything. And then this call, this is automatically called by Python when we pass in, you see layer and you pass in x. It's because layer is this myLinear class, and when we pass in x like this, it will be put through this call function that we can override. So x shape is batch size in features. So as I said, we need to multiply with the transpose of the weights, because weights is out features in features. Yeah. So we will multiply with the transpose of weights. So it will be batch size in times in out, because it will be transposed. So we get batch out features, and then add bias, and that's it. We can also, here in our class, we can add these parameters. So I can do that. But I need to recompile this, reinitialize, and now we have parameters here. So if I go params, you see we got the weights and we got the bias. Then let's make it Autograd compatible. So we want PyTorch to be able to automatically calculate derivatives, the gradients, the chain rule, so for backpropagation. So just here we will put nn parameter around these weights. So now those are learnable parameters, and same for bias, and that's it. That's the only difference. And now we will define forward here instead of call, so we can call this forward function later, and it will be same as this call. So it now works with optimizers, for example. So we can initialize this myLinear, my new linear, and we can create optimizer, which is stochastic gradient descent, pass in parameters. So if you try printing this, you will just get the iterator. This is, you cannot see parameters like this. And learning rate, and then some x random, and then target that we want to match. So x and target, and then for 100 steps we will make a prediction with x, and then so we want to map x to target. So we calculate loss of prediction minus targets squared and mean, so mean square error. We can maybe learn more about this loss later. Okay, and then backward step and zero gradients, and that's it. So now let's understand LayerNorm, but not only that, we will understand a lot about, you see here, normalization and squares and variances and stuff, which is very important. This is one of the most important things for you to understand intuitively. It applies to entire machine learning, so it's gonna be variance and mean and stuff. So we got this tensor. It has large values 10, 20, 30, and then this is small and centered, so centered around 0, minus 1, 1, so centered around 0. High variance between these values, 200 variance, and no variance, it's all same values. So original x, and then means, so we take mean along the first dimension number 1, which is the second dimension, which is here the last dimension, the innermost dimension. So it means we take mean of these numbers here and put it, and that's it. So we don't take mean across the entire thing, it's dimension 1, so it's just across these 4 numbers in this here. So we put it, that's 20, mean is 20, and then mean here, it's gonna be 0, and mean here will be 300, and mean here will be 1. What if I say 200 here? Mean is 266. So mean is sum of values over number of values. Then I got here variance and standard deviation. So this is a bit tough for me to understand as well, but here is how we understand it. So here below, in geometry, distance is based on squaring differences. So distance between two vectors. So we got the first vector, first coordinate, minus second vector, first coordinate, plus second coordinates here, and then we square and root. That's how you measure distance between two vectors. So variance and standard deviation are like measuring distance in high dimensional space. It can be not just 2 or 3 dimensions, it can be any number of dimensions, because vector can have any number of numbers inside features. From the mean, so you see here we will have so I'll show you. We have this is the formula, and this is the formula for the standard deviation. So standard deviation has this square root. So let's start with that. So you'll see that this formula is same as this formula. So we measure this kind of distance from the mean. So this is the mean. So the mean, so it would be like this. The mean for this first vector is 20. So you would go 10 minus 20, and then squared, and then plus 20 minus 20 squared, plus 30 minus 20 squared, because we have this sum here. So we are summing up all of this guy, in the end, divided by n, I believe it's just to normalize. So because you are adding all this stuff, you are adding it multiple times, it would just become a large number, but you don't need a large number, you want to keep it down. So this will make sure this n will make sure it's not so huge, and just to make it smaller, because you are adding so many numbers. Let's see, standard deviation of the first one it's 8, of the second one it's 0.8, third one is 160, and here there is no deviation at all. so it's 0. So there is a good analogy here. Imagine a group of people around a center point. Variance will give you the average square distance from the center. Hard to visualize. And standard deviation will give you the average real distance from the center. Easy to visualize. But actually, these are just approximations. So this is approximation of the average distance from the center and approximation of the average square distance from the center. So even though standard deviation is not exactly the average distance from the mean, it's close enough. In many distributions, especially in normal or Gaussian distribution, much more convenient for math and reflects spread in a way that penalizes outliers more, which is often desirable. So if you have these numbers, but you have a huge outlier like this, then it would the standard deviation would be a lot higher than just the actual mean. So it would, you would see that actually there is a lot of deviation inside of these numbers. It's not the same as, for example, having like how do I divide this? So 1500 and 1500 like this. So there is actually a lot less deviation here, even though the sum of them is same. So I just moved the number here. So this is also same sum, but the deviation is a lot bigger here from this number. So that's gonna be expressed by squaring. I don't know where it is, but anyways, we are squaring these numbers. So when you are squaring larger number, you will get a lot larger number than just squaring these two and adding them up. So mean is same in both cases, but deviation here is a lot larger, which it actually is. So it should be expressed that deviation here is a lot larger, even though the mean is same. So that's what square will do. It will express a lot larger deviation. Let's do more examples to get intuition. So we got tensor 1, 2, 3, and 10. Calculate mean. It's 4. So sum and divide by 4. So mean is 4. And then x minus mean. So it means the distance. So 1 to the mean, there is minus 3 in distance. So it's x minus mean. There is so it's minus 2, and then 3 minus 1, and 10, 6 when we subtract mean. So that's x minus mean. So now we take absolute values. So we put everything, make it positive. And then we take mean of these means, which is going to be 3. So this 3 says that the average distance of these elements from the mean is 3. So if the mean is 4, then the average distance from 4 here is 3. Because here the actual distance is 3, here is 2, here is 1, here is 6. And then the average is going to be 4. This is the true average distance from the mean, the true average distance. It's 3. And variance, you see variance is 12.5. So this is supposed to be approximated square of the distance, average distance. But not only that, as I said before, this will also make, so if there is a lot more variance, like you see here, if I put 1 and 12, now there is actually a lot more variance here, because mean is going to be even lower now. Actually, no, mean will be same, but now this 12 is even further away from this mean, which is 4. So now there should be even more variance here, which it will be because we are squaring each number in the variance. So I'll show you. Okay, so the average variance is 12, and it's in square units. Remember, the formula for variance is here, x minus mean squared, and then mean of that. So if you measure distance from center in meters, variance will be in meters squared. So if you want to get it back in meters, we need to take a root of this final result, which is going to be this standard deviation, which is 3.53. So you see here, I said that the average distance is actually 3, but we got standard deviation 3.5. And if I do this, if I say 2 and I say 1 and 12, now the mean should be same. So if I go here, mean should be same, but average absolute distance, it's gonna be 4 now, and this will be 21, and this will be 4.6 standard deviation. So now there is more deviation, even though mean is same, there is more deviation from the mean, which is gonna be this 12 instead of 10. So that's average deviation is now bigger, which is 4.6. So one thing was always confusing to me. So first, mean, that's actually very understandable. We sum up all of the elements and divide by the number of elements, and we get the mean. Okay, and that's the mean. And you cannot really do any other operations in that to that mean. If you, for example, divide that mean by 3, it will no longer be mean. It will just be like some other number that's like mean divided by 3. So there is like just one correct way to calculate mean. But I feel like standard deviation and variance are not so set in stone. I feel like we can choose many different ways to calculate standard deviation. For example, if we divide this formula or this number by an extra like divided by 3, we would still get the same behavior, like large deviation, large elements that have a lot of deviation would be squared, and then they would explode this number. So why exactly is it here 21.5? If it was like for the mean, it makes sense, but here, if I divide this number by 3 and the entire scale by 3, it would still have the same behavior, like big numbers with huge variation, when squared they will still explode this number. So this was not so intuitive ever for me, like why exactly like this number in particular for variance or for variance. On the other hand, this standard deviation is meant to approximate this mean absolute deviation, so mean the average distance from the mean. So if I divide this number by 3 or multiply it by 3, then the approximation would not be so correct. It would be a lot more distant from this. So I guess that's a reason that's a reason to choose this exact formula, I guess. But how well does this approximate? And maybe some other formula would approximate even better. That's the thing. I feel like the standard deviation, if anybody can explain, but I feel like it's just arbitrarily chosen, and just so we can like have a large number if standard deviation is large and lower number if standard deviation is low, but there could have been like any other formula to calculate that exact thing, and this one was chosen kind of randomly. Now we will see more examples here. So now we have some more examples. Uniform small values. They are small values. There is uniform distance between them, 1, 2, 3, 4, 5. Central small values centered around 0, but you see it's a bit stronger because this one cancels this one, but this one is now -1, so it's pulling towards negative -1. High variance, you see 10, 50, 100, 200, 500, okay? No variance, all same. And big outlier, 1, 2, 3, 4, and 100. So those are our tensors. Down below we will calculate the same things, mean, mad, standard deviation, etc. So the same things. And plot. So we should just look at this. This is the vector. The mean is 3. Standard, first of all, this distance from the mean is 21012. So 21012. Mean absolute deviation, mad, it's gonna be 1.2. But guys, why is it 1.2 if you can tell me? Look, distance from here is 2, and then distance is 1 and 0 and 1 and 2. So my intuition at first was that it should be 1.5 because we have 1 and 2. So the distance should be 1.5, and we got 1 and 2 on different side. So why is it 1.2? I thought it was wrong, but then I realized we have this 0 that has distance 0. So when we add all of them and divide by 5, we get 1.2, because here distance is 0, so it will bring it down from 1.5. Now this number, standard deviation, should be approximating this number. And we see that it is mistaken by 0.2. Here, so that's uniform small values. Let's see, we'll take this difference as the base. We'll see how other cases approximate this number well, or which ones are better, which ones are worse. So I feel like this one has almost same approximation. And these are central small values. So average distance from mean is because of this additional -1. And it's approximated very well. High variance. So we got, yeah, high variance. Now I feel like it's still approximating well, but I feel like it's a bit more different. So the difference between this and this is like a bit more than this and this. Because this would be like 74-64. And this is like 174 142, and this is because of the high variance. So this formula is specifically made to, if the variance is high, this number will be more like higher, and it will be much higher than this number if the variance is high. No variance, 0, everything is 0, and one outlier. You see, one outlier will do a lot of, so it's 39. But if I keep the means same, okay, let's remember 39 and 31. If I keep the means same, so let's just say 50 and 50. So now mean is same. It was 39, 31. Now it's 24. Now it's a lot closer. 24, 23. It's a lot closer actually. That's because as there is like one big number that's different, the variance is going to be a lot bigger than the average distance from the mean. Here I try to plot that, but I don't think we can learn anything useful from this because this is too small. Here we can't even see, but it's the same thing as I explained. It's just the same thing, so there is nothing new here. Now let's implement and understand layer normalization from scratch. So we have x, our tensor. So to calculate x normalized, what we will do is we will subtract mean from x. So imagine you have x is 1, 2, 3. So you want to actually make it around 0. So instead of 1, 2, 3, you want to make it -1, 0, 1. So you shift down by 3. No, by 2, sorry, by 2. 1, 2, 3, -1, 0, 1. So you subtract mean, which is 2, from each of the elements, so it's around 0 now. And divide by standard deviation. I'll explain how this is standard deviation, just trust me for now. So whatever the standard deviation is of x, it will be same when we subtract mean. So standard deviation here is going to be same as of x. So whatever it is, if we divide by that standard deviation itself, we will get standard deviation to be 1. So if it's, for example, 10, standard deviation, we divide by standard deviation this whole vector. Now we will scale down this whole vector so that standard deviation will be 1. Always, whatever the standard deviation is, because we will divide by itself. And so again now, how is this standard deviation? So we have variance, we know that that's variance. So we know that as a square root of variance is standard deviation. And this is just a small number. And so if this is 0, we don't wanna divide by 0, because if variance is 0, square root of variance is 0, so we have division by 0. We don't want that, we wanna add some small number so it's not 0. So we will see more examples here. And another thing we do in LayerNorm is we have this, so to get y, we have some weights and some bias. And these are learnable parameters. And so neural network will learn, in this case, to adjust these weights and bias, gamma and beta, in order to get some y value that's useful. And we'll see what a useful y value is. So we will see examples of all of this now. That's what we did here in this code. So we have my LayerNorm class. We have epsilon, a small number, not to divide by 0. And we have gamma, which is weights, and beta, which is bias. And gamma will be ones, because we multiply here. And beta will be 0. Zeros in the beginning initialized, because we just add that so we don't change anything. You see how epsilon is a very small number, 0.00001. And okay, let's see here. Call, so when we pass x through, you see this x will get passed through this instance. It will go through this call, so x. So mean is going to be mean. We calculate mean first. So this is, we get this x here, we calculate mean. This is amongst last dimension, so features. So it's going to be these features. For example, that's vector embedding, whatever. And then variance in the last dimension. And we'll see what this keep, dim, and unbiased is. So here, I have this explanation on this URL, which is my ChatGPT conversation. I find it a bit difficult to understand. So usually you want to keep it false. That's gonna work as our normal variation formula. And if you keep it true, then it's gonna be a change a little bit, like if you don't have entire x data, but you want to still estimate variance over x, even if you don't have entire x, then you're gonna set this unbiased to true. So it's gonna like divide a bit differently with n-1 over instead of n to try to do something. I'm not sure exactly, but for now I will skip this. And this keep dim, it will just keep the dimensions. So when you calculate variance, it will, so if you have 4 or 5, so 5 features, 4 samples in a batch, it will keep variance in a separate square of brackets, as opposed to just having like 4 numbers in one array, so for each batch. It will have a separate square of brackets for each variance number. And below that, we have this x norm is now x minus mean over torch. So this formula and this formula is what we actually have here. So what we just explained, those are the same formulas. But now you may notice I said that gamma and beta are learned parameters, like a linear transformation, but we are not making them here learnable. We are just initializing them to ones and zeros. So we will do that after I show you this example. So let's test it. Layer normalization is my layer norm and pass in 4. So this is normalized shape. So this is shape of the x norm after normalization. which I'm guessing it must be same as this shape features. So I guess we could have just passed in like the last dimension. If I do this and I say x dot shape, and how do I do this? I have no idea. Like this maybe? Yeah. So you see here, if I print x shape last dimension, so this will just show us the last dimension, which is 4. So we want to pass that into layer norms because we are using that to create gamma and beta, and we need to, when we are multiplying and adding, they need to be same shape as the last, this x norm, which is a bit weird again. Actually, it doesn't need to be last shape, just the last dimension needs to be same shape. And then these are gonna get broadcasted. So this is 3, 4, and this is just 4. So it will get broadcasted into 3, 4. So the row, the 4 elements will just get multiplied 3 times, or just copied 3 times. And here as well, it will get automatically broadcasted from just 1, 4 to 3, 4. Just gonna get same vector 3 times. And then it will be added to each of these 3 batches. I recommend, if you don't know what I'm saying, you should either ask ChatGPT to explain this, how this would get broadcasted, or you should try yourself writing some code, write some different vectors and try seeing what happens. And this is what you need to learn. It's not the latest papers, it's how this broadcasting works. And simple, fundamental, it's not even simple, it's just fundamental, but it can be a bit difficult to understand at first. Next, let's stack layer normalization and then goes to linear layers. So, my LayerNormLinear. So we just initialize my LayerNorm in features. As I said, those are gonna be features, yeah. It's gonna be same as this linear layer. So it's gonna be the last dimension of the x, of the input. Okay, out features, and then pass through the norm, and then pass through the linear and return. Guys, keep in mind, let me show you again. So if we have x with 5 batch size and 4 features, when we initialize this my LayerNormLinear, we will just, as input features, we will just pass this feature size. We will not pass this batch size, just feature size. So the last shape dimension, which will gonna be 4. And output features can be 2, whatever, it doesn't matter. So this 4 number of features will serve for both normalization and the linear layer. Then I put this in between, this new block in between this, so if you can't find this, don't get like confused. So PyTorch Autograd version. Here's a full trainable Autograd compatible version. Just the difference is here in gamma and beta, we will make them learnable parameters, and that's it. So we have this linear layer that we define here. So as you can see, this class is gonna combine linear class, initialization, and the layer norm. So we will just combine, put linear here, okay, initialize, and then forward pass, mean, variance, normalization is by calculating the deviation and all of this good stuff, x scaled. Yeah, so the neural network will learn, we will give it this additional kind of transformation for it to learn how it should transform normalization even better, for the linear layer to work even better after. So I guess this is also the linear layer. This whole line is another linear layer. But I guess it will just learn this. So we're just adding it one more linear layer here. So if we initialize, you see that this is the features dimension. It gets used as for gamma, for beta, and for linear in features. And output features, out features is this 2, And that's it, that's all we need. And then if we pass x through our layer, it will have both norm and linear layer combined. I will finish this video here. This notebook is available below, and in the next video we will be learning manual gradients, gradient descent or calculation of derivatives and gradients, and activation functions, and weight initialization, and a bunch of other fundamental stuff that we will be learning over the next 1 or 2 years to become really great at this research and engineering, so we can implement any paper and then understand what we are writing, what we are coding. And as soon as we read the paper, we will get a million different new ideas that we can try and improve, and it will be so easy for us, or a lot easier for us, to test a bunch of ideas and find good ones and publish papers. Find this notebook in the description of the video, and there will also be my full course that I'm building with you as we go, this full course for ML Researcher. I'm just going to put all of these notebooks there and videos. So check that out and see you in the next video.